Unit 2A, Lesson 2, Solving Systems of Equations. So we're going to talk about first in this lesson what a system of equations is. In its basic form is two or more equations that you're working with at the same time. We're going to be dealing with linear systems of equations. We have three different methods we're going to talk about to solving these systems, and we'll go through an example utilizing each of those methods. So first we're going to talk about the basics of what a system of equations is. It's a set of two or more equations with the same variables that you're working with at the same time. Okay, when solving a system, you are trying to find out where those equations overlap or where they have the same solutions, the same XY ordered pair if there are any. Systems can be linear or nonlinear. What we're going to work with in Algebra 1 is linear systems. Okay, at least to start out the year. Later in the year, we might work with some nonlinear systems after we go through some more different types of equations. When dealing with these linear systems, we're going to either have one, infinitely many, or no solutions to the linear system. We're going to discuss and go through three different methods that we can use to solve the linear systems in this lesson. The first one's going to be graphing. So if we have two linear equations, we're trying to solve that system, we're going to graph both equations on the same coordinate plane and try to find out where they intersect if they do. The second one is going to be substitution. We substitute one equation into the other equation and then just have a linear equation with variables that you can solve. The last one is called linear combinations. It's also referred to as the elimination method. So if we have two variables x and y, we try to get it down into one variable, either x or y, and then we can solve for a single variable. The first method we are going to discuss is the graphing method. We're going to use the graphing method if we have equations that are written in a way, in a form, that it makes it easy to graph. So looking at this example, both of these equations are in slope-intercept form, y equals mx plus b. They deal with integers or fractions that are not complicated, so it would be fairly easy to graph both of these equations on the coordinate plane. So we're going to do that, graph both of these, and then try to determine where they intersect, if they do. So we have the first equation, y equals 1/2 x plus 1. First, we have to plot the y-intercept, which is 1. From that point, we're using our rate of change, our slope, rise over run. This means we could go up 1 and over 2, which would be the same as down 1 to the left 2. So we just plot a few points and then construct a line going through all those points. Now that we have the first graph constructed, we want to graph the second equation, y equals -3x plus 8. So first I plot my y-intercept, which is 8, 2, 3, 4. Now from there I'm going to use my slope. If it's -3, that's the same as -3 over 1. And I can repeat that process, down 3 over 1, plot a few points, construct a line through those points. Now that we have our second line graph, we want to look at our coordinate plane. We're trying to determine where these two graphs intersect, where they have the same solution. So when I look at this point of intersection, that looks like it's at the ordered pair with an x value of 2 and a y value of 2. So the solution to this system of equations, what we were looking for in the end, that ordered pair, is 2, 2. So one thing we should do after using the graphing method, we could easily make a mistake when we graph. We want to plug in these x and y values to each of the equations to make sure we get a solution that works. So if I plug 2 in for x in the first equation, I would have 1/2 times 2, which is 1. 1 plus 1 gets me a y value of 2. So I quickly plug those values in. I get a statement that's 2. 2 is equal to 2. If I do the same thing in the second equation, I'd have -3 times my x value of 2. -3 times 2 is -6. -6 plus 8 gives me a value of 2. 2 is equal to 2. So we plug those x, y ordered pair into each equation. If we get a statement that's true, it's a solution to each equation. That means it's a solution to the system. The next method we are going to go through is the substitution method. We use the substitution method if we have one of our variables that has a coefficient of 1. So if we look at our equations, in front of x we have a coefficient of 1, a coefficient of -2, a coefficient of 2, and a coefficient of -3. So in front of our first x, in our first equation, we have a coefficient of 1. What we want to do is isolate that variable by itself. So rewrite this equation to get x equals. So if we rewrite this equation to get x isolated by itself, we get x equals 2y minus 3 halves. All we have to do is add this 2y to the right side of the equation. Now we're going to substitute this equal expression. We know 2y minus 3 halves is equal to x. So we're going to substitute this expression in for x in our other equation. So now that I substitute in my equation, I now have 2 times the quantity of 2y minus 3 halves minus 3 equal to -2. The reason we use this method, if I looked at this equation right now and I'm trying to solve for x and y, we have 2 unknown values. We don't know what x is, we don't know what y is. If we have 2 unknown values, we can't solve that equation. So we substitute this expression in for x because now we just have one unknown. We have one variable y. Well, that's what you've done so far this year. You've solved equations for a single variable. So to solve for y, first I would use the distributive property. 2 times 2y is 4y. 2 times -3 halves is -6/2, which reduces, simplifies to -3, minus 3y equal to -2. Combine like terms, simplify. 4y minus 3y leaves me with y. Then we would add 3 to the other side, so we get a value of 1 for y. Now we need to find the corresponding x value, so if we plug 1 in for y in our equation where we have x isolated by itself, then we'll get the corresponding x value. Plugging that value of 1 in for y, we get x equals 2 times 1 minus 3 halves. I would have to get a common denominator, so I rewrite 2 as 4/2. 4/2 minus 3 halves is 1/2. So this is the solution to the system of equations. The ordered pair 1/2, 1. Again, just like the last problem, once you get that solution, you should plug those x and y values into each equation to make sure you get something that's true. So we would have 1/2 minus 2. 1/2 minus 2, 1/2 minus 4/2 gets us -3 halves. 2 times 1/2 is 1. 1 minus 3 gets us -2. Plug each of those equations, or x and y ordered pair, into each equation, gets us something that's true. It's a solution to each equation, which means it's a solution to the system. The last method we are going to discuss is the elimination. This is also referred to as linear combinations. You use this method if you have coefficients in front of one of your variables, so either x or y, such that when you combine those expressions together, they're going to cancel out. So in order for those to cancel out, you have to have absolute values that are the same, where one's positive and one's negative for your coefficients, such as +5 and -5. If we combine those together, they would make 0, they would cancel out. So that's what we're looking for in the elimination method. For this particular system of equations, we could use the substitution method. We have a variable x with a coefficient of 1 isolated by itself. We could quickly substitute -2y plus 4 in for x in the first equation, go through, solve for x and y like we just did in the previous problem. But we're going to go through the elimination method. So what we need to do when using this method is line up your variables and constants vertically. Off to the right, you can see how I would rewrite these equations such that my x variables line up vertically, my y variables line up vertically, and my constants line up vertically. Now we're going to use the elimination method because, like I said previously, we want one of the variables to cancel out based on the coefficients in front of that variable canceling out, one being positive, one being negative. So what I mean is, if we look at a variable y, we have a coefficient of -2 and a coefficient of +2. Those absolute values are the same. One's positive, one's negative. So if we combine those together, they're going to cancel each other out, make a value of 0. So this y variable will cancel out if we add these two equations together, leaving us with a single variable x. If we have a single variable x, we can solve for that variable. So we're going to combine these two equations. I'm going to take 4x plus x, which gives 5x. When I add these two, -2, +2, that cancels out. So I'm left with 5x equal to 10. Now to solve for x, all we would do is divide by 5 and divide by 5, leaving us with an x value of 2. So that's why this is called elimination. We're eliminating one of the variables, also called linear combinations, because we're combining two linear equations by addition. Now I just have to plug in this x value of 2 into either of these equations. Doesn't matter if I choose the first equation or the second equation. I'm going to choose to use the second equation because I have smaller values that I'm working with. So I would get, plugging that value in, 2 plus 2y equal to 4. Then I would get 2y equal to, if I subtracted the 2 over, 4 minus 2 would be 2. Now I divide by 2, and I get a y value of 1. So the solution to this system would be the ordered pair 2, 1. Just like the last two examples, we should plug these x and y values into each equation to make sure they work. 4 times 2 is 8. 8 minus 2 gets us 6. If I take 2 plus 2, we get a value of 4. So this ordered pair 2, 1 is a solution to each equation, which means it's a solution to this linear system of equations. This lesson had a lot of information. First, we had to talk about what a system of equations is, and we talked about the 3 different methods: graphing, substitution, linear combinations. Went through an example showing each of those methods. Okay, so make sure you understand the process for each of those methods, as well as when we are likely to choose one method over another, looking at the way the system is set up, the equations are organized, and the coefficients, things like that.